Alright, so very good afternoon to everyone. A very good afternoon to all of you, my dear students. A very good afternoon to all of you. So, guys, my name is Dr. Shankar Sir and I am your physics educator. So, guys, in this session, we are going to have a complete revision of the properties of solid. Alright, so in this session, we'll be having a complete revision of the properties of the solids. So, guys, we have already completed this chapter on this channel. So now, hello Harsha, very good afternoon. So in this session, we will be doing what? We will be completing this whole chapter in one go. Okay, so we are now going to talk about the properties of solid. Okay, properties of solid. So it is sort of a revision session. Are you getting my point? So we have done this chapter on this channel already. Okay, so if you want to go into details of this chapter, you can refer to the detailed videos of each of the topic, right? But if you want to have a quick revision of the whole thing, okay, or if you are looking for one stop session, one shot session in which most of the important things are covered, then this is the right place where you are. Okay, so all the live students, welcome to the session. I hope you are doing well, and now let's begin with the session. So basically, in this chapter, what do we need to talk about? So in this chapter, ultimately, we have to talk about the effect of the force on a body. Right. So basically, see, when there is a body, okay, when there is a body, somewhat like this, let's suppose, okay, and if you are applying some force on this body, so basically this body, so see, as I always say, force is a kind of thing. When it is applied on something, it will definitely do something to that thing, right? Like in this situation, when you apply a force like this, when you apply some force like this on this particular body, this is going to have a displacement. Okay, this is going to have a displacement. Now, when it is displaced from this particular place to this place, what is going to happen then? We'll talk about the velocity, we'll talk about the acceleration, right? And we'll talk about the kinematics part. And further, if the body is having some acceleration, we can find the force, that is F is equal to ma. So this is one part of the physics that we already have seen in the Newton's law, right? So Newton's law, kinematics, okay, all this thing we have seen, right? Now, if there is a body, okay, if there is a body and if a force is applied like this and it is applied like this also, right? Now, in this case, when two equal and opposite force are applied on a body, two equal and opposite force are applying on the body, here the body will have some deformation. Okay, so you can call it P, you can call it F, anything that you want. I prefer calling it P. Okay, you can call it anything. Don't get it confused with the pressure or power or something. This is our force. So basically, when this force is applied on this body, it will tend to deform this body, and that is why we call it a deforming force. Now, prior to this chapter, when you see the Newton law of motion and something, that force basically we assume. Okay, so in NLM, what we do, okay, in NLM, what we do, so we assume rigid body. Okay, we assume the body to be a rigid body. Okay, now what does this rigid body signify? So rigid body means when the force is applied on this body, there is no deformation of the body. Okay, no deformation due to force. Okay, no deformation. So if something is having no deformation, okay, if something is having no deformation, that we call in physics a rigid body. And see, practically there is no body which can be called as a rigid body. Understood? Right? So see, in there we consider a rigid body. Now in this part of physics, we are interested in finding out that if a force is applied in such a way that it will deform that body. Okay, so this chapter is analyzing that. effect of the force on some body. So see, in this, what we are interested in finding out, we are interested in finding out the stress, okay, strain, okay, deformation, right? So load is there. Okay, so basically this chapter revolves around these four things. Okay, like if a force is applied on a body, what will be the stress in that body? What will be the strain in that body? What will be the deformation of the body? Okay, due to that particular load. Okay, and further we'll talk about some more things like energy. Okay, so basically it is the outcome of these things. So basically this chapter involves a study of these four things. Okay, what is going to be the stress in a body when it is subjected to some force, right? What will be its deformation, what will be its strain, and what will be something like that. Okay, okay, so see, first we need to understand something known as the elasticity, right? See, this is as I am clarifying that this is not a detailed chapter. So if you see like the main sessions of this particular chapter, I have taught everything in very detail, but in today's session I'll be little quick, right, and covering the most important things. Okay, because this is a one shot session and I'm trying to have it completed the whole thing in some 2 hour 30 minutes or maximum 3 hour, right? So see, when we say elasticity, so when I say elasticity, so you might be thinking that something is coming in your mind like rubber. Okay, so if I ask you which is more elastic, rubber is more elastic or steel is more elastic, what do you say? Which is more elastic? Normally, like if you go to buy some rubber or something, right? What we say when we go to buy some rubber or something, we sometimes say, "Sir, give me some elastic," isn't it? The shopkeeper, right? So, what do you think, the live student? Which is more elastic? Which seems to you more elastic, rubber or steel? What do you say? Okay, so Tanu is saying rubber. Harsha, what is you want to say on this? What would you say on this? Hmm? So, Harsha, you are also telling rubber. So, see, this is the first thing that I want to understand. Rubber is not elastic as much as the steel. Okay, now please try to understand this. So, elasticity, when you say something is elastic or elasticity, basically it refers to these two things. Basically, something is elastic, that means it is following these two things. So, first of all, what is the elasticity? So, it is the tendency to oppose it is the tendency to oppose any change of shape any change of shape, size, okay, uh, dimension. All, like when I say shape and size, so it covers the dimension, the tendency to oppose any change of shape, size of a body. Okay, so when we say some body is elastic, okay, when we say some body is elastic, the first thing, yeah, Harsha, it is not right. I'll just explain why it is not right. The tendency to oppose any change of shape or size of a body. Okay, so the material which is having more tendency towards which resist. Okay, so you believe that every material behave differently, isn't it? Like Harsha, Tanu, me, and anyone else present in the. So we all are different individuals. On a given same situation, would we act in the same way? What do you say? Very unlikely, no? Like God has made this physical world like this only. Even God has made us like this only, that all of us are in some way different to each other, isn't it? Although we may look like same, we may have the same height, we may have the same features, but even then we are unique, right? Now, same way, the God has made each and every material unique, right? He has given, or she has given, or the Almighty have given you know, different properties to each of the material. So even under the same condition, all of them behave differently, right? I hope you believe this, no? Steel would be behaving differently than rubber. They behave differently than aluminium, than copper, than plastic. Plastic have a certain different kind of a behavior. Even liquids are involved, like water behaves in a other way, mercury will behave in some other way, isn't it? Honey will behave in some other way, right? So all materials are unique only. Okay, so basically in this particular part of physics we are trying to understand. Okay, and lately if you like see the application of this very small chapter of 11 physics, you will see the whole mechanical and civil engineering. Although you are going to the field of medicals, but in these days medicals are also, very much in medical also these things are very much used. Like if you see, like previously, now every day some more improvement is happening. Recently I visited a dentist, so he showed me like, sir, this implant is there, this is made of titanium, this is made of this thing, right? It has this much titanium, like that. Even in the implants, right, what we try, see, we always try to mimic the god, right? And see, like it is very very unlikely or very challenging to understand each and everything how the worlds operate, right? But still as a human being we always try to do so, isn't it? See, every material has some elasticity. Are you getting my point? So you are saying diamond also behave elasticity or not? So every material shows some elasticity, right? But the question is still what limit it is going to show the elasticity. I'm going to explain to you. But you answer me, like out of rubber or steel, what do you feel? And you Tanu also, what do you feel out of these two, which will have more tendency to oppose the change of shape and size when suppose both are subjected to the same amount of load? What do you think? What do you think? Which will have the more tendency? Which will have the more tendency to oppose the change of shape and size? Steel or rubber? Tanu is telling me steel. What about you, Harsha? What are you telling me in this? बताइए. Harsha, what do you think? Will rubber show more tendency to oppose the change of shape or size, or steel will show? Hmm? Steel, obviously, right? So rubber, if you apply the force, and let's suppose the same amount of force you are applying to the steel, what will happen? The rubber will deform easily compared to steel. So this is very obvious, isn't it? Now, this way, if I consider like this particular concept to judge the elasticity of these two materials, definitely the steel is on the winning side, isn't it? The steel is on the winning side. Now, the second thing, that is what we mean by elasticity. Okay, so the tendency the tendency of a material, the tendency of material to regain is original shape, to regain its shape original shape after removal of the load, after removal of the load, right? So the second thing that we refer to as elasticity is the tendency of material to regain its original shape after removal of the load, and this happens to be up to elastic limit. Okay, what is elastic limit? This is a material property, I'll be explaining you. So see broadly, what if I want to tell you, like up to elastic limit the force are not very high, isn't it? This is the main thing I want to tell you. Now, what do you think? Now, what do you think? Now, please try to feel it. We have a specimen, let's suppose, of steel. We have a specimen, let's suppose, of rubber. Now, we are applying the same force. We are applying the same force. Now, which will have the tendency to regain its original shape? If you feel it is again steel, are you getting my point? Right? It is again steel. So if you are applying a small force, if you are applying a small force and see up to elastic limit in steel, if you see it visually, so you won't be able to notice any deformation. Are you getting my point? Like you are seeing it from your naked eye, and you are seeing it, you will feel that like with this much force, the steel is not showing any deformation, but there is some deformation, though it is very less, like zero point 0.1, 0.2 mm, zero point 0.4 mm. Like that is why when you are solving the question of the chapter, you normally get answers like deformation happened to be 1.2 mm, zero point 0.8 mm, right? 1.25 mm. So would you be able to see some 0.1, 0.2 mm deformation? No, sir, you won't be able to see. So steel, when you are applying the force up to elastic limit, steel will regain its shape, original shape, even faster than that of the rubber. So which is more elastic? Beta? Steel is more elastic, although it seems not, like when we vaguely think of that which is more elastic. Are you getting my point? So steel is more elastic than the rubber. Okay. Yeah. Yeah, deforming force when it is reproved. Yeah. So see, so you must have seen this tendency, that you are pulling something, pulling something, pulling something, and when you remove the force, some part of the deformation is regained. Okay. So up to elastic limit, what happens that when you remove the force, if your material is within the elastic limit, that you haven't crossed the elastic limit, so basically when you remove the force, all of its shape will be regained, right? It will going to have its original shape. Understood, beta? Understood. So, like in any way you see, steel is more elastic, right? This is how physics work, right? Understood. So, see, understanding the physics is like somewhat different. Like, for example, if I quote one more example, like not in this context, like in thermodynamics, we do. So, if in a closed room, if in an insulated room, in a closed room, if I open the door of the fridge, will the temperature of the room is going to decrease or increase? What do you say? if the if the room is completely insulated, okay, when the room is completely insulated and you open up the door of the fridge, what is going to happen? The room temperature is going to increase or decrease? Any answer? What do you think? See, what I'm trying to tell you, that how you must see the physics, how much you see the phenomena, right? So if there is an insulated room and if you open the door of the fridge and you left it open in a closed insulated room, what is going to happen? Will the temperature of the room increases or it is going to decrease? What do you say on this? What would you say on that? Tanu is telling me decrease. What about you, Harsha? You understood the situation, na? We all must have the refrigerator at homes, isn't it? Hmm? So if I kept the door open, if I keep the door open, the temperature is going to, now it seems to you like it is going to decrease, but it is actually going to increase. Are you getting my point, Bida? Are you getting my point? So if you apply the first law of thermodynamics, you will be able to understand that. I suppose there is a closed room. Okay, there is a closed room and there is a refrigerator inside. There is a refrigerator inside. So this is how the physics is. Like sometimes the things that you see normally are not in that way. They doesn't work that way. Are you getting my point? So what you are thinking that, sir, if we kept the door open of this refrigerator, some cool air is going to enter the room, and due to the coolness or the coldness of this air, the temperature of this air is, since it is low, So basically what is going to happen, it is cool down the temperature of air inside this room. But this is not the case. See, you must have seen del Q is equal to du plus del W. This is the first law of thermodynamics. Now since the room I said is insulated, this is going to be 0. So du is going to be, see, and now see, refrigerator is taking electricity from outside, isn't it? Right? Electricity from outside, isn't it? So electricity is a form of high grade energy. It is a form of pure work. Okay, so when the work is added to the system, when work is added to the system, you must have know that when the work is added in the system. So let's suppose electricity, it's a work of electric work or electricity work. When it is added to the system, it is going to be negative. This is the sign convention. Yes or no? So if you haven't read the thermodynamics, you are going to see this way, right? So when the electricity is going to enter the room, that means work is adding up in the system, and work being added in the system is taken as negative. And del Q is 0, so it is 0. So from here, du will be WE. That means du is positive. Du is positive, that means internal energy of the system is increasing. When internal energy of the system is increasing, considering it as ideal gas, that is the air, the temperature will increase, right? So what you were thinking and what actually is happening in this situation is quite different, isn't it? So why I am telling you this? Because see, when we say elasticity, people think, okay, rubber is very elastic. So we stretch it, it is stretched, right? And we call it in the shops also, we go and ask for elastic. Bhaiya elastic dena na. We say like so, isn't it? But this is not the way physics walk, right? So from the first law of thermodynamics, we can see that when you leave the refrigerator door open in an insulated room, the temperature of the room, instead of decreasing, is going to be increasing. Understood? You got my point, what I'm trying to tell you? That this is how you must see the physics. This should be not like what you are seeing may not be true in the eyes of the physics. Did you get my point? Yes or no? बोलिए ना भाई. Hmm. Did you get my point? Acha, you got it. Right? Harsha? Okay. So shall I proceed now? Okay. Shall I proceed now? Yeah. So basically, in this part of physics, beta, we talk about what? We talk about the situation of static equilibrium. The situation of static equilibrium. Okay, so what is the situation of static equilibrium? So let's suppose on a body, there are multiple forces acting. Okay, what do we mean by the static equilibrium? So there are multiple forces acting. There may be some moments acting on this. So many things are happening with the body. Okay, so many things are happening with the body. Now, when we assume the body to be static equilibrium, it simply means that the summation of forces in any direction that you take, the summation of forces about any direction that you take is going to be equal to 0. Okay, okay, so the net force on the body will become 0, right? That is why no F is equal to ma in this chapter. Are you getting my point? Right? So we know, like from the Newtonian physics, like if any force is left on the body, if there is any net force acting on the body, it is going to be equal to m into a. But in this case, there is in any direction, in no direction there will be any net force or the resultant force. The summation of force in any direction that you see is going to be 0, whether it is x, y, or any other direction. And similarly, there is no net moment on the body, because if there is net moment on the body, it will try to rotate the body, isn't it? Isn't it? Yes or no? So when we say that there is a problem of this particular part of physics, one thing is that we are having to use these equations of equilibrium. Like for example, let's suppose we are having a body. Okay, we are having a body, and on this body a force P is applied like this. Okay, so now for this to satisfy, for this question or for this physical problem to lie in this particular scope of physics, so there must be what? There must be a reaction also. So that is why we assume one side as fixed and we call that this is the reaction to this force. Understood, beta? Is it fine? Yeah. Okay. So now in this case, what is going to happen? It is going to have the deformation somewhat like this. It is going to have the deformation somewhat like this. Right? Okay. Okay, and now please understand this. So see, now what we are interested to do. So force we already have. So what are the other things that we are trying to find here? So you said that, so in this particular part of physics we are interested in finding the stress, we are interested in finding the strain, we are interested in finding out the stress, strain and the deformation. We are interested in finding out these things: stress, strain and deformation. Right? So now see what is going to happen. What is going to happen? So this is going to be, so see, when this kind of force is applied here, so this is going to be L plus delta L, right? There will be some increase in the length of this particular body and there will be some decrease. So let's suppose this is the dia. Let's suppose this is the dia D. This is the dia D. So there will be some increase in the length and do you feel that there is going to be some decrease in the diameter, right? So I'll call it delta L. Okay, and there will be some decrease in delta D, isn't it? Do you agree to me or not? Let's suppose that this is having a circular cross section having initial dia phi, right? So it is a normal tendency now. So when you pull something, remember, see, I'll try to explain something. So when you pull something, what do you do? When you pull something, it is stretched. Okay, its length increases, and if its length is increasing, you will see that is cross section, right? Cross section maybe. So see, this is my pen. Okay, so this is the length. What is the cross section? This, which is perpendicular to the plane of a screen. If I rotate it, it will look like this. Are you getting my point? I'll just give you something. So see, I'll just show you. So I'll just take out a page. So see how we have to see the thing. See what happens. So world is three-dimensional, no? World is three-dimensional, right? Now when the world is three-dimensional and I want to, or we want to see the world on the page, on a paper, on a screen, on a whiteboard, on a blackboard, okay? Now in that condition, so this is a 3D thing, no? This is a 3D thing, right? It is a circular, three-dimensional circular thing, right? It is a three-dimensional circular thing. Now see, first of all, we must try to see this in two dimensions. So this is actually three-dimensional. It is actually three-dimensional, but I want to see it in two dimensions. So when I want to see it in two dimensions, I have a two-dimensional screen, I have a two-dimensional board. Now when I am having a two-dimensional screen on a two-dimensional board, so I cannot show this body in one plane. Okay, so how we do it? So when we cannot show this body in one plane, then what we do? What we do with it? We see it from the front, we have to take two views. We have to see it in two orientation. Now if I see it from the front, I'll see this part, right? I'll see this part, okay? And this part, when I see from the front, it will look like the rectangle as you see in the first, in this one. When you see the rectangle, it will look like this one. Are you getting my point? Now, to know the cross section, so what is the cross section? So this is the cross section. See this circle. This is the cross section, what we call. So this is obviously the length, and this is the cross section, this side. Right? Now, if I want to see, because see, if you see this first figure, When you see this first figure, you don't know that whether it is a rectangle, it is a triangle, it is a circle, or what is it, right? It could be a square also, right? It could be a square also. Are you getting my point? It could be a rectangle also. Now for that, you have to see it from this side. This is what we call as from the side. So from there, this look like a circle. So normally a body in physics, since it has to be represented in two-dimensional plane, we need to take two views of it. Okay. Now, do you believe this? First of all, you both of you, please tell me, and all the other live students also. First of all, if you haven't subscribed the channel, please do subscribe also. That will be of good help to us. So now, when you see this, now when you are going to see this, okay. So when see first try to feel this thing. So when we are pulling something, when we are stretching something, like if I stretch this body, so this is having no brittleness, right? No ductility. So when you are pulling something, when you are pulling some body, so do you feel that if a elastic body is there and you pull some elastic body, you will see that the length, if increasing, the cross section dimension or diameter is decreasing. Do you feel so? And if I compress something, see this kind of a load is what we call as the tensile load, which has a tendency of pull, right? And when we have a tendency to push something, that means the compression, like you are doing like this. So if you are applying the force like this, now see, if you are applying the force like this, see, now if we are applying the force like this, see what is going to happen when you are applying the force like this. So you will see that this body will tend to have a decrease in its length. This is going to have a decrease in length, right? And since its length is decreasing, you will see that its diameter is increasing, right? So if this is L and this is D, this is D. So see, this phi is a symbol that this is a circular. Okay, so when we have with some dimension, when phi is given, that means it is the diameter, right? Now, when we apply the force like this, Vida, so definitely it is going to show some contraction. Okay, and when it is contracting, you can, I think, feel very clearly that the diameter or the cross section dimension is going to be increased. Understood, Vida? Please answer me. Akbar, very good afternoon, and hello and welcome to the channel. My name is Dr. Shankar Sir, and I am a physics educator. So in today's session, we are going to have a complete revision of the chapter of properties of solid. Okay, so it seems to me that you are new to the channel, and you and Tanu and Harsha, you can please tell me if you get this concept or not. Right? Acha, Akbar. So welcome to the channel, Vita. So since you are new, let me introduce myself. So my name is Dr. Shankar Sir, and I have done MTech and PhD from Indian Institute of Technology, Roorkee. Have qualified the GATE examination, and I'm teaching for last 11 years for JEE and NEET aspirants, and I teach physics. Okay, so in this particular session, we are talking about the properties of solid, right? So just to give you a context. So see on this channel, what we try to do. So in this channel, we are running physics, biology, chemistry. All three subjects are going ahead. And in physics, we have completed a few chapters. Units and measurement we have completed. Motion in a straight line, motion in a plane, vectors, mathematical tools, right? Properties of solids we already have completed, but this session is a one shot session. देखिए अकबर जी, मैं कोशिश तो यही करता हूँ, ठीक है, और कैसा पढ़ाता हूँ ये तो आपको जज करना पड़ेगा दोस्त, समझ रहे हो? ठीक है, अपनी तरफ से देखो, मैं कोशिश करता हूँ कि मैं बेस्ट पढ़ाऊँ, और कोशिश यही करता हूँ कि मतलब जितना बेसिक से हो सके उतना ही बेसिक से पढ़ाऊँ। जैसे अभी मैं आपको एक बहुत बेसिक से पढ़ा रहा हूँ इस चीज़ को, ठीक है ना? तो आप थोड़ी देर अगर सेशन देखें और सेशन को फॉलो करें तो आप ये सब चीज़ों को बेटर वे में जज कर सकते हो. ठीक है. So shall I continue? So basically is part of physics mein, and also but this is an English channel, so I'm bound to teach in English. So this is an Unacademy channel and this is an English channel. So this is also I want to clarify to you. Okay. So I'll be explaining the things in English, and if at all by any chance if you're not comfortable with any explanation, you can ask me to tell you that in Hindi. Sounds good? कोई भी बात अगर आपको नहीं समझ में आएगी तो आप मुझे हिंदी में बता दीजिएगा, मैं हिंदी में समझा दूंगा, उसमें कोई इशू नहीं है. Okay, so see what we are talking about here. So when a load is applied like this on a body, so I was saying that see when load is applied on some body, what happens, it will definitely do some change. So normally in the Newtonian physics what we do, so some force is applied on this body. So this body will have, this will move from its position and it will show some displacement. Now once it is having some displacement, we talk about the velocity, we talk about the acceleration, we may talk about a jerk also, right? And whenever somebody is having acceleration, then F is equal to ma comes up and other things come up, right? Now this is one part of the physics. Now when the force is applied like this, having an static equilibrium, what is meaning of static equilibrium? That the forces are applied in a way that they are equal and opposite, like this one. See the white, see the image in white. So you will see that on this body, two equal and opposite forces are applied. Okay, this is what we know as the static equilibrium situation. Now in this condition, the body will tend to show some deformation. So in this Raj, hello, good afternoon, and welcome to the session. My name is Dr. Shankar Sir, and we are dealing with the properties of solid in this session. Right? It's a complete session, and we'll try to give you a revision to this chapter. So if you want to go for the detailed chapters on this channel, you'll see that you can see my detailed session of this particular part of physics. In this particular session, I'll be a little quick, right? Because I want to complete the whole of this in this session only. Are you getting my point, Bida? So now see, so in the Newton's law of motion part, in the Newtonian physics part, we talk about the rigid body. That is the body which cannot have any deformation due to the force. In this part of physics, we talk about when the force is applied on a body in such a way that it deforms that body. So now the body is no more rigid body. Okay, it is no more rigid body, it is a deformable body, and we are applying the force that is the deforming force, right? So now on a body, so in this particular chapter we talk about, loosely we talk about these things: stress, strain, deformation, load, energy. Okay, so we have spoken a little about elasticity, and now I'm coming to the point. Okay, so see, on this body when we apply the load like this, see, the length is going to be increased, the diameter is going to be decreased, right? This is how things work, no? Like if you practically think of a rubber or an elastic body, when you stretch something, when you stretch something, it is going to have an increase in length but decrease in the diameter. This happens, right? And similarly, if you compress something, like if you are applying the force like this, what will going to happen? It is going to show a decrease in length, but its cross-section dimension. Cross-section dimension could be diameter, it could be width, it could be depth, right? Okay, so I have shown you the cross-section also. Na? So like what is the cross-section? So if there is a body like this, what do you want to tell me, Aisha? Pulfi? What is that? So see, this is like this now. This body is like this. So if you want to see, so this is the cross section which goes perpendicular to the plane of the screen, right? Because the world is three-dimensional and we are trying to learn it in two dimensions. This is how things work, no? Otherwise, how will you be able to present this physical world, right? Okay. Now, see what we have to find here. So we are interested in finding the stress, the change in length, the strain. Okay. Now you try to understand this. So there is a change in the length also. There is change in the, depth also, right? So here I'll be defining you a few things. Okay. So first of all, what is strain? Okay. First of all, what is a strain? So a strain is change in dimension. Okay. No, there is no perfectly rigid body in this world. Change in dimension upon original dimension. Change in dimension upon original dimension. Okay. See, there is no perfectly rigid body in this world. There is no perfectly plastic body in this world. There is no perfectly elastic body in this world. Are you getting my point? In the practical physical world, there is no body which is perfectly rigid, perfectly elastic, perfectly plastic. It is just a myth, right? Like in the level that you read the physics, you may not know that whatever formula we are learning, it is for isotropic material. Are you getting my point? It is for isotropic material, right? Right. Okay. So you may not know it. So in this world, there is no material which is exactly isotropic. What is meaning of isotropic? Beta? Isotropic means that a material is having independent properties. Like the elastic properties are independent of direction. But in practical world, it is not like that. Okay. Wonderful. Okay, so now the strain is change in dimension upon the original dimension, right? Now I'll be defining you here two strains. So see, when you want to move ahead with this chapter, you must be very clear about these two things because I have seen that students are very much confused in these two things. So one is longitudinal strain, okay, and one is the lateral strain. One is the lateral strain. Okay, one is the lateral strain. Like for example, if it this body, if I say, so I need to learn here, I need to see here the two things. One is longitudinal strain and one is lateral strain. One is longitudinal strain and one is the lateral strain. So let's suppose that we have applied the load on this body in this direction. So let's suppose we haven't applied the load yet. So this is length L and this is D. Okay, this is D. Are you getting my point? Or let me make it like this. So, okay, I'll just try to do it in 3 dimensions so that you understand it in ones. Right? Let's suppose we are having a body somewhat like this. Okay, we are having a body somewhat like this, and this is L. Okay, this is B, and this is D. Okay, this is D. So now this body, when it may be subjected to, when it will be subjected to load, it may have strains in any of the direction. It may have the strain in any of the direction. Are you getting my point, Bala? It may just a moment, huh? Just I cannot see your chest properly. Yeah. Okay. So now, when some load is applied on this body, there may be change in D, there may be change in B, and there may be change in L. Okay, so if I refer it with the normal coordinate system, that is x, y, and z. Okay, x, y, and z. Do you have any issue in saying that the strain that happens to be in the y direction is delta d by d? A strain that happens to be in the z direction, it is delta b by b, and a strain that happen to be okay, a strain that happen to be in x direction is delta l by l, delta l by l. Now I have a very simple question for you guys. Now out of it, which one will you call as the longitudinal strain? Okay, I'll call the longitudinal strain by epsilon and the lateral strain by epsilon L. Now please tell me which is going to be the longitudinal strain and which is going to be the lateral strain. Please answer me. बताइए. Akbar, Harsha, Tanu. Which is going to be the longitudinal strain which is out of these three, which is going to be the lateral strain? Please answer me. Okay, Tanu is saying that's the, so this is EX is what? अरे बोलो ना भाई, Tanu, is it lateral you are talking about, the longitudinal you are talking about? And what about you, Harsha? Akbar? Okay, so you are talking about longitudinal. So according to Tanu, the longitudinal strain is epsilon x. And what about you, Harsha? And Akbar, if you are still there in the session, and other, live students? Very good, Harsha. And what about the lateral ones? So, sir, obviously, when we are saying that epsilon x is the longitudinal one, the epsilon y and epsilon z are obviously the lateral ones. Now, please try to understand this, beta. Please try to understand this. We don't know. The answer to the question is that we don't know. We cannot tell. अरे बोलो ना भाई, are you getting my point, sir? We cannot say that which is the longitudinal and which is the lateral. We cannot say. Now, please understand this. See, first confusion that a student is having, they think that the longitudinal strain is the strain happen to be in the length. Are you getting my point? The longitudinal strain is not the strain happen in length. People say, sir, in length, so it is longitudinal, so it is happening like this. See, please understand this. If I make the load like this, beta, if I make the load like this, let's suppose I am applying the load this way. Now, in this way, beta, this will become the longitudinal strain. Delta D by D will become the longitudinal strain. And what do we mean by the lateral? Lateral means the strain in the direction perpendicular to the longitudinal direction. A strain in the direction perpendicular to the longitudinal direction. So the lateral strain will be the strain in this case in x and z direction. Beta, please understand this. See, when you say longitudinal strain now, when you say longitudinal strain, and when LBD are not very different from each other, longitudinal strain is basically the strain happened in the direction parallel to the application of force. Are you getting my point? Okay, and in this case LBD are not very different, otherwise this would become shear force. That is some different picture altogether. Are you getting my point, beta? Okay, so before you comment upon longitudinal lateral, you just have a look upon that what is the direction of the force, okay, or what is the kind of the force. Did you get my point? Yes or no? Right? Now, when they say nothing, let's say they say that a load P is applied on a body of length something, then you may consider, okay, then you may consider that the load is applied like this. Okay, the load is applied like this. Okay, and let me assume that this is a rectangular body having a dimension of the cross section as B and the dimension of the cross section as D. Are you getting my point, brother? Are you getting my point? Now, when the load like this is applied on this body, what we are interested to find now? Sir, we are interested in finding the delta L. Now we understand since the load is this, so we can say the longitudinal strain is delta L by L and the lateral strains are delta B by B and delta D by D. So what are the lateral strains? Lateral strains are the strain happen to be in the direction perpendicular to the direction of the force or the longitudinal direction. Understood, beta? Understood? And this force that we call this is the normal force. This is the normal force. This P is the normal force. So why we are calling it as normal force? Normal means what, beta? Normal means perpendicular. Normal means perpendicular. So see, when you call the force to be normal and when you call the force to be shear, so basically this depends upon how it is oriented with respect to the cross section. So when it is normal to the cross section, it means it is somewhat like this. Please observe. So see, if I make this body in 3 dimension, see, when we try to see this in 3 dimension, see what is going to happen. When we are trying to see this in 3 dimension, see, I am fixing one side. So see, when we call the force as normal, so this is that force. So normal to what? Normal to this area. Normal to this area. That is why we call it normal. Samriti, namaste. Welcome to the session. My name is Dr. Shankar Sir. और आज के सेशन में बेटा हम बात कर रहे हैं प्रॉपर्टीज ऑफ सॉलिड की. ओके, सो हैव यू कंप्लीटेड दिस चैप्टर बेटा? क्या आपने ये चैप्टर कंप्लीट कर लिया है? बताइए. हैव यू कंप्लीटेड दिस चैप्टर बेटा? अगर आपने इसको नहीं कंप्लीट किया तो बेटा आप इस सेशन को एक बार देख सकते हो. Okay, anyway, so basically this is the normal force we are talking about. Now see, again I said that the God has given similar nature to everyone, be it earth, be it steel, be it aluminium, be it any liquid. When you are applying some force of the body and the force is trying to deform the body, राजदीप किस चीज का एक्सेप्शन बताइए? किस कॉन्टेक्स्ट में एक्सेप्शन होगा बताएं? मैं आपका कॉन्टेक्स्ट नहीं समझा. किस चीज का एक्सेप्शन? हाँ, तो भैया जैसे हमारे को अगर कोई मान लो हमारे हाथ को ऐसा टेढ़ा करने पे लड़ाई होती है ना बच्चों में. सो व्हेन वी आर फाइटिंग अमॉन्ग्स्ट ईच अदर बीइंग अ किड, so sometimes like we hit something, we try to do like this. Okay, now you might have felt, okay, that when you try to deform something, be it even your body, right, it is going to some resistance to that deformation. So this is the very nature of everything. Okay, this is a very nature to everything to resist is the changes in its shape. Are you getting my point? And this is how fluid is different from solid, right? Like fluid is unable to resist the shear stresses. That is why it flows. Okay, so I'll be, when I tell you the fluid thing, I'll be coming to that. Now see, due to this resistance, this body is going to have some stress, right? So see, since the normal load is applied here, so basically it will have a normal stress. And what is the stress in general? So stress is basically the internal resisting force per unit area. Okay, it is internal resisting force per unit area. So what is this F? So internal resisting force, okay, internal resisting force, and A is the area of cross section. Okay, so since this force is perpendicular, on so I'll have to so since this force is perpendicular to this area of cross section, we call it what? We call it the normal stress. Are you getting my point? The stress due to this load is normal stress because the load itself is a normal load. Okay, so very easy, no? Very easy. But sir, what we do? So sir, you are writing internal resisting force. You are writing internal resisting force, and now we are going to denote it like this sigma. This is the general notation, though different book denote it differently. Right? I'll be using this sigma. So see, sigma is equal to force upon area, but we can comfortably take it P upon A. Or is a P is internal resisting force? This is the external force. This is the external force, na? But see, this is how you see the formula, sir. Why you see this formula? Because this is valid within elastic limit, which I prefer writing proportionality limit. So within I'll tell you what is the difference between proportionality limit and elastic limit. So within proportionality limit, what happens? This external force, okay, a body within this proportionality limit, the body will have the same internal resisting force as the external force. Are you getting my point? That is why we say the stress in the case, in this whole particular chapter, external, see, we read what stress is internal resisting force per unit area, but we do what? We use the external force upon area when we are solving the problems, right? So why it is so? Because we are talking within the limit of proportionality. Are you getting my point? Stress is sorted. Stress is sorted. Now look, let's come back to this thing. So now what we are interested to find? We are interested to find the strains, the change in dimensions. Stress is already sorted. Okay, stress is already sorted. To see, let me make this again. Right. Now see. Now see. A force is applied on this body, and this obviously want to change the length of this body. It will increase the length of this body. It will have the effect of extension or increase in the length because of the nature of this force. Now we are interested in finding that change in length, right, or that strain. So longitudinal strain will call delta L by L. Okay, delta L by L. Are you getting my point, brother? Are you getting my point? So see what is going to happen. See, so there are two things here. One is the Hooke's law. Okay, one is the Hooke's law. So what is the Hooke's law? Any student can tell me what is the Hooke's law? So Hooke's law says, I'll just tell you. So see, what is the statement? So it says the corresponding stress is proportional to corresponding strain. Corresponding stress is proportional to what? It is proportional to corresponding strain within the limit of proportionality. Okay, so see, sir, in NCERT, in our books, it is written as elasticity. So actually, see, for some materials, the limit of elasticity and proportionality are same. Although when you go for your higher studies, you will be able to understand that they are different. So I prefer to write limit of proportionality. So remember, the Hooke's law is valid within the limit of proportionality. Understood? So corresponding stress is proportional to corresponding strain. So that means, see, understand this. Now see, Hooke's law says corresponding stress is proportional to corresponding strain. So with the help of Hooke's law, what we are going to relate? We are going to relate the normal stress with the normal strain, that is the longitudinal strain. Are you getting my point, Bida? Normal stress is proportional to longitudinal strain. The normal stress is proportional to longitudinal strain, but remember this happens within the limit of proportionality. Right? Okay, so anyway, this is already we have written. So now stress is proportional to strain. Now remember which stress? Normal stress. Which strain? The longitudinal strain. That is, the strain happened to be in the direction parallel to the direction of the load, if the load is normal, right? Now, whenever we let go of the sign of proportionality, when we know that there is a constant that comes up, what is that constant? That constant is known as the Young's modulus, okay? In this case, right? And sometimes it is also called as modulus of elasticity. Modulus of elasticity. So if at all we have the stress and strain, we can find the modulus of elasticity. Are you getting my point, Buddha? Okay. So basically, what is the relevance of this modulus of elasticity? So this is a material property. As in the beginning of this session, I told you that every material is unique in its own way, right? So if you apply a load on a particular body, so it will show different deformation or strain if it is of steel, if it is of aluminium, if it is of copper, right? Different materials show different strains when subjected to the same load, right? Even they have the same area. Do you believe it or not? Right? I want to ask you one thing. Like, imagine that we have some aluminium, okay, or we have some rubber, and we have a steel. If we apply the same load on both the bodies, will they deform by the same amount? Very unlikely, no. Right? Otherwise, the whole world would have been made of the same material only, na? Sir, this mobile I am having, where I am seeing your chats. So this mobile is made up of glass. Why it is made up of glass? Why it is the screen is made up of glass? Because for this particular application, the glass is the best, isn't it? Sir, I am having this. You see, I am having this water bottle. This is made up of steel. Why it is made up of steel? Right? Because there is some purpose to it, no? There is some purpose to it, isn't it? Okay, this is my wallet. So this wallet, very bad condition, sir. Wallet is very bad condition, no? You may say, but just I want to tell you. So this is of leather. Are you getting my point? This is of leather. Okay. Okay, so now see, every material have a different property. That is why different materials are used for different applications. We are making different things of different material. Why? Because we are manipulating their properties, right? So basically, this modulus of elasticity, or like later we'll be seeing the bulk modulus, we'll be seeing the shear modulus. So all these are elastic properties, and they basically govern or give you an insight that when a load is applied on a body, how much it is going to deform. Did you get my point? Yes or no? So it is an elastic property. And Young's modulus or modulus of elasticity is particularly, so Young's is the name of the scientist basically. Okay, it is nothing like it's being young or something. It is the name of the scientist, right? It is the name of the scientist. So see, stress is proportional to strain. So sigma is equal to E times the strain. Understood? Now see, from here what we can write, so stress is equal to force upon area, and E or strain is change in length upon original length. So from here we can make one formula, that is delta L is equal to PL upon AE, right? PL upon AE. So this is a very useful formula in this part of physics. Now did you get this point or not? Please answer me, all of you, all the live students. Am I clear up to this point? Yeah. Please answer me. All of you. Okay. All of the live students, did you get this formula? You might have memorized it, right? Now I hope you have got this formula. Yeah? Harsha? Rajdeep, you were, acha, you haven't read like this. Okay. So I hope you are liking it, no, Tanu? Harsha, what about you, Vida? Rajdeep, exception, what exception you were talking about? You haven't replied afterwards. Samriti, uh, Raj, Akbar, if you want to respond to it. Right, all of us are comfortable, isn't it? Right, isn't it? Yeah? Well, let's make one question then. On NEET PYQ it is. Clear? Okay, so we'll do one question. Huh? What about the rest of you? Very good contents. So let's try this question. I'm very sure we can do. Yeah? Please try to do it. I'm very sure if we try to, we can do. Come on, please do. What is the answer? I'll just write the options also. Yeah. The option is not visible. Please do it. Very, very simple question, isn't it? Hmm. Then you have answered. What about the rest of you? So this is a small chapter. Come on, do it. Please do it, beta. Harsha, contents. Please answer it. We just have seen it. What is the problem? Please do it, Bida. Come on, please do it, bhai. क्या बात हो गई ऐसी? Tanu have done it already. अरे करो ना भाई. We have to complete this today. Harsha, you have answered something. Point 3. Okay, I'll do now. So it says elongation of a steel bar 1 meter. Now please try to listen to me first of all. See, if you want to find the elongation, you don't have any other formula than this. Okay, any other formula than this. So delta is equal to PL upon AE. Okay, so we do not have any formula other than this. So P is 1.5 into 10 to the power 4, right? Length is 1 meter upon area. So area, so 1 meter, so we'll put it 1000 because ultimately we need to answer in mm, right? So this is going to be 1000 upon area. Area is 1.5 centimeter square. So 1 centimeter is 10. So centimeter square will become 100. Okay. And Young's modulus is 2 into 10 to the power 11. 2 into 10 to the power 11. So from here we can get the delta, isn't it? So see, 4, so 11 I have to write 10 to the power 3, right? Yes or no? Okay. So why I am doing 2 into 10 to the power 3? So see, when you are putting everything in mm, so you must take care of the dimensional homogeneity, right? So this is in Newton per meter square. So I have to change it into mm, right? Okay, so I have to multiply it. So it is not 2 into 10 to the power 3, but it will be 2 into 10 to the power 5. So I have to multiply it 10 into 10 to the power minus 6. So 10 to the power minus 6, this will become 10 to the power 5. So from here we can get the delta, right? So see how many zeros. So this is 7, 7. All the zeros are gone. All the zeros are gone. This is gone. So we'll have 1 by 2 mm. So 1 by 2 mm is 0.5. Okay. So remember, see, you just have to use this formula. We do not have any other formula than this. Are you getting my point? Please answer me. बोले भाई. Are you getting my point? Please answer me. अरे बोले ना भैया. बोलिए हर्षा, कहाँ गलती हो गया था? गॉट इट और नॉट? प्लीज आंसर मी. चलिए एक क्वेश्चन और ट्राई करते हैं. तो इसके अलावा देखो कोई फॉर्मूला नहीं है. अंडरस्टूड? देयर इज नो फॉर्मूला देन इन दिस. Let's say we have a pulley here. We have a pulley here, and on this pulley we are having, so you must have seen problems like this, no? So there is some wire like this. Okay, very well. This is 2 kg. Okay. So now let's suppose that the breaking stress of the wire, breaking stress in the wire, okay, very well. Breaking stress in the wire is 2 into 10 to the power 5 Newton per meter square. This is the breaking stress of the wire. Okay. Okay, so you need to find the minimum, cross-sectional area, find the minimum cross-sectional area, of wire so that it doesn't break, okay. I'll give you some options. Now please try this one. I'm very sure we can do. Okay. Now come on, please go for it. Please go for it, beta. Come on. I'm very sure if we can do it if we try to. Please do. Come on, please try it. See, I'm very sure we can do it. Yeah, waiting. Waiting. Come on, do it. Come on, do it, beta. So no Harsha, any answer? Come on, please do it. Please do it, beta. Any answers? Any answers? So how we can do it? Please try to do. So I'll do it now. See, breaking stress in the wire. Now see, there is something very obvious. So see, stress in a body must not be increasing. The stress in a body must not be stress in a body must not be more than the breaking stress. Okay, because see, if the stress in the body becomes more than the breaking stress, the wire is going to get broken. It will going to be break, right? Okay, it is going to be break, right? So see, breaking stress in the wire. So see, what is going to happen? So now this is 4 kg, this is 2 kg. This is 4 kg, this is 2 kg. So see, there will be some tension in the wire, isn't it? There will be some tension in the wire, obviously. So the wire will have, let's suppose, the tension T. So what is going to be the stress in the wire? So stress in the wire is going to be the force on the wire, that is tension upon the area of the wire, and it must be less than equal to the breaking stress, isn't it? Because obviously if the stress exceeds the breaking stress, the body or the material or the component, the wire is going to get failed, it is going to get break. So we don't let that happen. So see what will happen. So first of all we have to find this T. So how we can find this T? So see, what we can do. So see, this is T. So if I use the equilibrium, so G is always downward. So can I say, so G is always, so see, in this kind of arrangement, what is going to happen? So this is going to go like this. So the acceleration will be in this direction, isn't it? The acceleration of this is going to be in this direction. Now see, if I write the dynamic equilibrium for the body of 4 kg, can I write like this? See, I'll just write it here. So it will be 4g, that is weight is acting downward, 4g and minus t, because the tension is upward, minus 4a. What is 4a? It is the moment, it is the inertia force, F is equal to ma, isn't it? Right? So this is going to be 4a, right? So now if I write the equilibrium for this 2 kg body, now see its acceleration will be in upward direction. Why? See, when 4 kg, 2 kg is there, so it will be going like this. Now 4 kg will be falling downward, so the 2 kg body will move upward direction. So acceleration of this 2 kg mass is upwards. So what will happen? So this will be 2g, this will be 2g, right? Weight, okay, minus t, and this is going to be 2a. So 2a and 2g are in the same direction, so plus 2a is equal to 0, isn't it? Plus 2a is equal to 0. Yes or no? Please answer me. Yeah, is it fine or not? Please answer me. Right, I hope yes. So see, solving these two equation, we can have the t, right? Solving these two equation, we can have the t. So from here, when we solve, so see what we are getting. So see, we can have, so if I multiply this whole equation by 2 and then I add this to the first one, I'll add it to the first one. So we will be getting the t is 8g by 3, right? 8g by 3. Are you getting my point, beta? So what is the tension in the wire? So when we are solving this equation, we are getting 8g by 3. Okay, so now what will be the stress in the wire? So T will be 8g by 3 and the area we have to find, and it is less than equal to the breaking stress. So breaking stress is 2 into 10 to the power 5. Okay, so G, if we consider the G as 10. Okay, so from here we can find this area, and this area will come out to be, from this equation, the area will come out to be 1. When we solve it, we'll be getting 1.33 centimeters. So very simple, no? Very simple, very simple. Yes or no? Please answer me. Boliye. Harsha and Tanu, did you got it? Please answer me. Yeah? Please answer me, Buddha. Did you get it or not? Please answer me. बोलिए. Did we get it or not? Please answer me, Buddha. Yeah? All the live students. Okay, so Tanu, you have got it. What about you, Harsha? So will you be able to deal with these kind of a question in which you are asked about the stresses or you are asked about the strain, deflection or something like that? Please answer me that. Will you be able to deal with them? Yes or no? The live students, please answer me. Will you be able to deal with all these things? Yes or no? बताइए भाई. Right? Ah, okay. The live students, you can please respond to me. I hope you have got this point. Yeah? Ah, now let's move ahead. So now what we have, so now if you understand this, so what we have done, so we have been speaking about this, that's when we are having a body like this, right? Right, and the load applied on this body is, let's suppose P, this is L, and let's suppose the cross section dimensions are B and D, width and depth, B and D, right beta? B and D. Now in this case, see what is going to happen. In this case, what is going to happen? So we have P, we have L, we have B and D. So see, we have sorted out the stress, right? That is force upon area, that is P upon BD, cross section area we have to take. We have sorted about the strain, longitudinal strain, so it is sigma upon E, and we are sorted about the change in length, sir. It is PL upon A. It is PL upon A. Now, sir, what about the lateral strain? Now, see, this is the longitudinal strain. From longitudinal strain, you got the change in length. But what about the lateral strain? What about the lateral strain? Okay. See, when a body is subjected to such a load, what will happen? Its length is going to increase, but its cross-section dimensions is going to have some decrease. Its cross-sectional dimensions are going to have some decrease, right? Now see, from where we are going to get this lateral strain. So this lateral strain, we are going to get from a concept of Poisson ratio. From a concept of Poisson ratio. Are you getting my point? Okay, Poisson ratio, right? Or we call it Poisson. Tanu, you are asking for the break. We'll do. Just after this Poisson ratio, we'll do. No worries. Okay. So see, Poisson ratio is what? So we can represent the Poisson ratio. So see, Poisson ratio. See, from the Hooke's law. From the Hooke's law, what we did? From the Hooke's law, we get the longitudinal strain. From the Hooke's law, we got the longitudinal strain and the Poisson ratio. With the help of the Poisson ratio, we are going to get the lateral strain. We are going to get what? We are going to get the lateral strain. So what is the Poisson ratio? So see, it is the ratio of the lateral strain with the longitudinal strain with a minus sign. So it is again a elastic property. This is again a elastic property. So different material process different elastic properties. So different material process different Poisson ratio as well. So the Poisson ratio is going to be minus of lateral strain to the longitudinal strain. Are you getting my point, beta? It is minus of lateral strain to the longitudinal strain. I hope it is fine to everyone. Okay. So let's see one question, see how they sound. I'll just show you. So Okay, let's try this one. So after this question, I'll give the break. Please do it. Correct, please do it. Very simple question. I'm very sure we can do. Tanu, Harsha, you may please try to solve this question. Please do it, Bida. What is the answer to this question? Please do. Okay, so Tanu have answered something. 0.3. Okay, let us see. So it says a metallic rod of 500 mm length and 50 mm diameter, when subjected to a tensile force of 100 kilonewton at the ends, experience an increase in its length by 0.5 mm. Okay, so let's suppose we are having a metallic rod and its length is 500 mm, and its length is 500 mm. Okay, and due to this load, how much load is applied? Sir, 100 kilonewton load is applied. Okay, 100 kilonewton load is applied. So when it 100 kilonewton load is applied, you can see that there is some change in length. So this is 50 mm. Okay, there is some change in length, and that length changes is 0.5 mm, right? And change in dia. So this is reduce. So reduce will use when something is contraction, when the dimension is getting reduced. What we are going to do? We are going to use minus sign, right? Now we are asked about the Poisson ratio. So what is the Poisson ratio of a material? So Poisson ratio is the lateral strain to the longitudinal strain. So the Poisson ratio will be 0.5 divided by 500, right, upon, so this is 0.5 upon 500 upon point minus of 0.015 upon 50. So how much we are going to get from here? So see, what is the formula? So minus of, so why this is minus in the first place? So why you are using minus here? So see, so see, this is due to the opposite tendency. This is due to the opposite nature or opposite tendency of the longitudinal and lateral strain. So as I told you, so when we are stretching something, when we are elongating something with the force, right? The other dimension, the perpendicular direction, is going to have a decrease, right? So see, if the longitudinal strain is elongation, it is positive, the lateral will be negative and vice versa. If you compress something, the reverse is going to happen. Understood? Reverse is going to happen. So this minus sign is due to the opposite tendency. This minus sign is due to the opposite tendency, right? Okay. So see, when we have this minus here, so this minus and minus are going to cancel out, and now I can see that it is 1 by 3. So it is going to be 0.3. So the Poisson ratio here in this case will become 0.3. I hope it is fine to everyone, right? Okay, understood. So now let's move ahead a bit. Acha, acha. Yeah, Tanu. So we'll have the break now. No worries. So see, we'll start at 5:30 again. Okay, so break, and the session resumes at 5:30 p.m. All right. Alright, so welcome back. Anjali, very good evening. Okay, Tanu, I am back too. So, guys, we had a break of 15 minutes, and till now in this session, we have completed the poison thing, the Hooke's law, right? So, Anjali, very good evening. Uh, so, beta, in this session, what we are doing? So, in this session, what we are doing, beta? In this session, we are trying to have a revision of properties of solids. So on this channel, we have completed this chapter, but I wanted to have and the students wanted to have a one-shot session of the chapter. So we are trying to do that. So have you completed this chapter, properties of solid? Yeah. So my name is Dr. Shankar Sir. I am the physics educator, and I don't know whether you are following this channel or not. So I'll just give you a brief introduction. Okay, wonderful. So this is me. This is a brief introduction about me. And on this channel, we are running physics, biology, chemistry, and we are trying to come up with question sessions, the learning sessions, and all this. So you can subscribe the channel, and we can go ahead. So now let's talk about the thermal stresses. Okay. So, see, in this chapter, the second thing that we must, so before thermal stresses, so see, we have come to understood this formula. Now to find the elongation, there is only one formula, that is PL upon A, okay? And we have found the stress, that is force upon area. There is no other formula than this, okay? Now there is one case, that is the elongation of a prismatic bar. So see, I'm going to be a little quick because see, already we have discussed all these things in the session, in the descriptive session. So there you will see the proofs and all of these things, right? So here I'll be just giving you the direct expression. So see, what is the elongation of a prismatic bar due to self weight? What do we mean by the prismatic? So prismatic means that the body is of uniform cross section throughout the length. Okay. So let's suppose we are having a bar like this. We are having a prismatic bar like this. Now, due to the self weight of this prismatic bar, so let us assume that gamma be the weight density. Okay. Gamma be the weight density. Right. Yeah, Anjali. See, Anjali, if I may, see, this is the session in which I am trying to see the description of this particular. So, if any question belong to this chapter, otherwise, see what you can do. You can come in a practice question session, right? So there you can ask me any question. But see, because see, this video is having we need to discuss about the properties of solid. Right. So if any question is from this particular part of physics, then you are most welcome. Right. But if it is from other part of the, so I just request you to come to the practice session. That will be a good place. Right. Okay. Yeah. If it is from this chapter, you can definitely ask. Otherwise, you can come to a question practice session, or you can mail me the question. I'll reply. This is my mail ID. Okay, you can have a note of it. UTripathi@me for mechanical .iitr IITR Indian Institute of Technology Roorkee.ac.in. Okay, sounds good. Okay, so see, now if we are talking about the elongation of a prismatic bar due to self weight. So see, every material have some density. So let's suppose that gamma be the weight density of this particular bar. Okay. So see, what is going to be the elongation? So if you want to see the proof of it, you can go to the detail section. So when we prove it and when we find it, so it is gamma L square by 2E. right? This is the length, this is the L, okay, this is the L, and the elongation due to self weight will be given as gamma L square by 2e. Understood, beta? Yeah, thank you, Anjali. Thank you for understanding. Right, so this is going to be gamma L square by 2e, where E is the Young's modulus, L is the length, and gamma is the weight density. Now, please understand this. See, if we see at some x, now see, this is one way of writing this formula, but the other way could be, so sometimes they give you the weight density. Or if the weight density is given, what is the unit of the weight density? It is rho g upon volume, isn't it? So Newton or kilonewton per meter cube, right? So in the terms of the weight density, if you find the elongation due to self weight, you will have gamma L square by 2e, right? Now please understand this. Yeah, thanks. So now please understand this. If I write the load at some particular section, if I write the load on some particular section, see what it will be. So what shall be multiplied? So normally what units of the force or the load we prefer? What is the unit of the force or the load we prefer? So sir, obviously we prefer the unit of Newton or kilonewton. Now, if you want to make this, if you want to make this in Newton and kilonewton, what shall be multiplied with the weight density, sir? So obviously, sir, volume must be multiplied. So what is the volume? If I write the load on this particular x section, it will be gamma AX into x, okay? Because A into x is the volume. So the load on this section is going to be gamma into A into x. If you want to find the stress on any section, so we can write it on the x section. So it is going to be the force on this section upon the area of this section. Karan, if the doubt is from the chapter of properties of solid, you can definitely ask. I was just telling this to Anjali also. So, better see, on the channel we are having the practice sessions, right? We are having the question session. So when you are having a doubt, you can ask me in the practice session. Because see, if I start dealing with the doubt in the academic session, firstly, this is not allowed. This is an academy channel. So see, we have to follow some sort of guidelines. Okay. In practice session, you come, in question solving session, you come, you can ask me anything, right? But see, in the learning session, when we are talking about the properties of solid, so if the question belongs to this particular chapter, you are most welcome, right? Otherwise, I was telling Anjali also, so this is my mail ID, right? So you can mail me over here, utirparty@me.iitr.ac.in. Okay, okay, okay. So no, nothing to be sorry about, Karan. See, it is like, see, I wanted to, see, please, see, we, what to do? I am also like, you know, compelled to say so. Otherwise, I wouldn't have denied. So, any doubt from this topic? If you have, then please go ahead. Right. And see, almost most of the, if you see, the channel will come up with the practice sessions, right? Practice question, PYQ session, right? So in those sessions, you can definitely ask, right? Okay. So see, elongation due to self weight. So if we want to find the stress on any particular section, the px is going to be gamma ax, that is the force upon area. So what will be the stress? It is going to be gamma into x in terms of gamma, right? Now, see, if I see this expression gamma into A into x, the load due to self weight, the maximum force will be at x is equal to L. So Pxx, since it is gamma Ax, and we understand that x is varying from 0 to L. X is varying from 0 to L. This Pxx will be, so at x is equal to L, this force is going to be maximum. So we are going to call it P, and this will be gamma into A into L. So sometimes it is also given as W. So when they say that the self weight is W, please understand this. When they say in the question that the self weight is W, okay, and the unit to the self weight is kilonewton. So they are referring to this gamma into A into L. That is the maximum self weight on a particular, bar or a body. Understood, beta? Understood. Now, if I rewrite this expression, see, delta of self weight is gamma L square by 2e. But we also come to understand that the self weight, if given in the unit of kilonewton, it is W is equal to gamma into A into L. So gamma will be W by AL. W by AL. So we can put it here. So it will become W L square upon 2AL into E. So this will become WL upon 2AE. So elongation of a body due to self weight. Remember, if the W is given, in kilonewton, okay, W is the self weight given in the kilonewton. So if the self weight of a body is given in a kilonewton, self weight of the body is given as W kilonewton, you can have it placed in this particular formula, and you can have the elongation due to self weight. Speak hello, very good evening. So did you get this point? Yes or no? Tanu, Harsha, and all of you, and if you are watching it, did you get it or not? Okay, okay, sir, Tanu, you got it. So the self weight is W kilonewton. Is it fine, beta? Please answer me. Yeah. Then, right now see, if I say, yeah, speak. Hello, good evening, welcome to the session. My name is Dr. Shankar Sir. What is your name? Okay, wonderful. Now, if on a body says, now let's suppose we are having a body, okay, and on this body there is a load. Let's suppose there is a load of 100 kilonewton, okay, and the self weight of this body is also 100 kilonewton. Self weight is 100 kilonewton. हाँ बताइए बेटा, इसी अगर इसी से रिलेटेड डाउट है इसी चैप्टर से तो प्लीज बताइए. तो ये है मान लीजिए 1 मीटर एंड एरिया इज 100 mm स्क्वायर. स्पीड प्लीज बताइए बेटा, डाउट बताइए. इस चैप्टर में डाउट है तो बताइए. अगर किसी और चैप्टर का डाउट है तो उसके लिए बेटा क्वेश्चन सेशन में आना पड़ेगा. ठीक है, बताइए. सेल्फ वेट में डाउट है? And Young's modulus is also 200 GPa. So please give me the elongation of this body. इस body का क्या elongation होगा ये you need to give me. क्वेश्चन सेशन बेटा एक कल हुआ था, अभी आगे होगा. हाँ हाँ, वेटिंग चलो. मेरे ख्याल से मे बी टुमारो डे आफ्टर टुमारो. सी वी रेगुलरली हैव द क्वेश्चन सेशन. अभी अगर आप चैनल फॉलो कर रहे हैं so yesterday we had a PYQ session, day before that we have a practice session, day before that also we have a practice session, day before that also we have a practice session, right? So see, when there is an academic session on this channel, so what happens, like today's session, what is the topic today? Properties of solid. So I am bound to not go other than this topic. Are you getting my point? See, this is an academy channel, and I hope that all of the students are also understanding that we are working in an organization and we have to follow some guidelines, right? Okay. So if अगर आपका डाउट इस चैप्टर से रिलेटेड है तो यू आर मोस्ट वेलकम. ठीक है, चलिए, कैन वी ट्राई दिस क्वेश्चन. सेल्फ वेट भी है और एक 100 किलोन्यूटन लोड भी लग रहा है. प्लीज आंसर इट. थैंक्स फॉर अंडरस्टैंडिंग बेटा. Okay, let's try this one. I'm very sure we can do. Please do. Then have you attempted this question? Then any answer to the question, beta? See, now it's very simple. See what we have to do. So now in this case we are having self weight also, and we are having an axial load also. So what will be the net elongation of this body? The net elongation of this particular bar would be the elongation due to this axial load, and it will be due to the self weight. It will be due to the self weight. Okay, it will be due to the self weight. So axial load. So for axial load, what is the formula, sir? It is PL upon A. It is PL upon A plus what is the elongation due to self weight formula? So see, in this the self weight is given in kilonewton. So when it is given in kilonewton, yeah, I'm doing it. So see, very simple. See what we have to do. देखो इसमें एक बड़ा सिंपल कॉन्सेप्ट चलता है, पहले तोड़ने का फिर जोड़ने का. ठीक है, कैसे तोड़ोगे जोड़ोगे, मतलब what we have to do, we have to apply the superposition. See what happens, the elongation of this body is going to due to the axial load also and due to the self weight also. Do you realize this speed? Yes sir, we do, right? So what is going to be the elongation due to the axial load? It is PL upon A, we just have seen it, and the elongation due to self weight is WL upon 2AE. So what is going to be the net elongation, beta? So it is going to be, so what is the axial load, sir? It is 100. For kilonewton, we can have it 10 to the power 3. L is we having. So see, we are having all the data. I'll just change the page. So it will be, so what is the P? It is 100 into 10 to the power 3. So L, that is 1 meter, that is 1000 mm. Okay, if we do in mm, divided by area, area is 100 mm square, right? And Young's modulus is 200 GPa. So 200 into 10 to the power 3 Newton per mm square plus W. W is again 100 kilonewton. L, okay, upon 2. Area is 100 mm square into E, that is 200 into 10 to the power 3. So when you will be solving it, you will be able to get the answer. So what students are getting confused in it. So when they are saying that the self weight, see I tell you, they are saying the self weight is 100 kilonewton. So when they say the self weight is 100 kilonewton, they think that they are referring to this 100 kilonewton. So because this is axial load, this is not the self weight. This is not a representation of a self weight, but it is a representation of the normal load, or you can say axial load. Are you getting my point, beta? So now, if the axial load is there, you will be able to find the stress and the deformation and the strain. If there is self weight alone, you are able to do that. And if self weight and axial load both are combinedly acting on a body, you will be able to get the net elongation even then also. Isn't it? Did you get my point? Yes or no? Yeah? Please answer me, madam. Did you get this or not? Speak. Speak up. Please speak up. Acha, Tanu, you have got it. Good, 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 good. Okay, then. Okay. Now, please understand that there is one more concept of the thermal stress. Okay. One more concept is there of the thermal. So, see, for detail, see, all of this I have taught in detail in the descriptive sessions you will see on this channel. Okay, so if you want to know more about all these things, you can go there. So in the descriptive session, I have given, of the conical bar also we have found. For the tapered bar also we have found. Okay, so we have done so many things, right? So if you want to have the more detailed information about these topics, you can go there, right? And have a watch on those sessions. You can simply watch those sessions. Understood? Okay. So now let's talk about a bit of the thermal stress. Now please understand this. Let's suppose there is a body. Okay, let's suppose there is a cuboid or there is a body somewhat three-dimensional we are having like this. Okay. And see, if I increase the temperature, if I increase the temperature of this body, let's suppose by delta T. Now, if I increase the temperature of this body, would you think so? What happens, like in general, what happens when you increase the temperature of something, right? So every material show a tendency. So if the temperature is increased normally, the body will show the tendency of expansion. Do you agree to it or not? Please answer me. Do you agree to it? Yeah. Please answer me, Vida. Right. So see what happens. Let's suppose this is L, this is B, and this is D. Okay. So see, every material have different response to the change of temperature. Right. So if I increase the temperature of this body, definitely it is going to expand and it will see the expansion. It will see the expansion in all the direction. It will see the expansion in all the direction. Okay, it is going to have a expansion in all the directions. So see, different materials again, different solids again are going to expand differently, or they are going to have the change in dimension differently for a given change of temperature, and this is governed by a property of the material known as the coefficient of thermal expansion. Coefficient of thermal expansion. Are you getting my point, beta? So see, it is again a material property, and basically it governs that when the temperature of a solid is increased, how much is going to elongate, and if it is not permitted to elongate, what is going to be the stress in the body. Okay. Okay, so now when the temperature is increased, it is going to show some change in the dimension. So now due to temperature, see, this is very, very simple. Due to temperature, the length is going to be changed by the amount alpha delta T into L. the width is going to be changed by the amount alpha delta t into b, and d is going to be changed by the amount alpha delta t into d. Very, very simple, isn't it? Now from this relation you can also get the unit of this alpha. Sir, how come? So see, change in length, what is the unit of the change in length? Sir, it will be meter. What is the unit of length? It is meter. And what is the unit of this change in temperature? Sir, it could be Kelvin. So what is the unit of this? So sir, 1 upon Kelvin, right? 1 upon Kelvin, right? So basically this coefficient of thermal expansion for different materials, it is different. Okay. Okay. So now see, please understand this. So see, if the temperature of the body or the solid is increased, what is going to be the change in any of its dimension? We can find if we have the alpha, and if we have the change in temperature, and if we have that dimension. Hussein, very good evening. Welcome to the session. My name is Dr. Shankar Sir. Okay. Now, when the temperature of this is increased and it is free to expand, please understand this. It is free to expand when this body is free to expand. Okay, what happens if it is free to expand? That means there is no restriction. So a body is there, you increase the temperature, it wanted to expand in its all the directions, in all its dimension. So see, what is going to happen then? What is going to happen then, beta? It is when it is free to expand, when it can expand in each and every direction, there is no restriction to its expansion or the deflection. Basically, it will have no stress, right? It will have no stress. See, the stress is what? Internal resisting force per unit area. So simple logic, when there is no resistance, right? Something is deforming and nothing is stopping that deformation. There is nothing that is stopping that strain. So what will happen? What will happen? There is no reason of a stress to come because there is no resistance. Understood? So unless there is a restriction to expansion, okay, there will be no reason of stress to come. Okay, so there will be no stress. So again, if I say, see, let's see in two dimensions. So let's suppose this is L and this is D. This is D, and if I increase the temperature of this body, if I increase the temperature of this body, what it is going to do? So it is restricted from one side. So what? If it is restricted from the other one side, it is going to elongate from the other side. What is the problem? No problem. So again, there is no restriction to its elongation. So it is again free expansion. And when there is free expansion, whenever body is free to expand, so there is no reason of stress in that body. So again, there will be no stress in this body. Are you getting my point? Okay. Are you getting my point? So again, I would say that if you want to go into much depth of it, see, I have given so many cases in 3 dimension, 2 dimension of thermal. We have sorted out a lot of things. So you can go for the detailed session. You can go for the detailed session. So see, now here is the length. Now here is the length. So if I fix this body from both the sides, right? And now if I increase its temperature, so what is going to happen? Now if I increase the temperature of this body, now in this case, beta, what is going to happen? So in this case, what is going to happen? It will try to expand in the x direction, but it will not be able to expand in the x direction, right? So in this case, some thermal stress will come. Okay, thermal stress will come, and that thermal stress will have some value, and it will be in x direction. Why? Because the elongation is restricted in the x direction. Okay, now in this particular case, when you find the thermal stress, it will be alpha delta T into E, right? So this is no formula of thermal stress, but this is the mostly asked case. Okay, okay. So see, you can go to the more descriptive session. I have derived this formula, and we have find the thermal stresses in different cases also. So how we got this formula, for that you have to go to the detailed video. Okay, so see, it is obviously a one-shot session. So one-shot session is there. So I'm just giving you a brief context. Okay. Okay, so see, I think this will be sufficient for this because see, strain energy is quite a big topic. So for strain energy and stress strain curve, which is left to be taught, and bar connection. So now see, you can if you have subscribed the channel, you might have watched it. If you haven't watched it, you can see the session on the strain energy and the stress strain curve, very detailed session. So strain energy, stress strain curve, bars, these are not those topics which I can do, very quickly, right? So see, the most important things I have covered in this session as far as the properties of solids are concerned. Okay, so guys, I hope you have enjoyed the session. So the live student can tell me that if you have enjoyed the session or not. Did you find it useful or not? Yeah. So mostly in the next session, I'll come up with the complete revision of the three chapters, okay, that we have covered till this session on this channel. Okay, so that could be in that session. I'll be trying to cover the most important things of the chapters of units and measurement, right? The chapter of uh, motion in a straight line, motion in a plane, vector. Okay, so guys, thank you for watching the session. I hope you have enjoyed the session. You found this session useful to you. So please, I'll request you to subscribe the channel, share to your friends, like the videos, and help us growing the channel. So with this, thank you very much. Have a good day, and we'll see you in the next session.